Algebra of complex numbers. Hello everyone, welcome to my channel. My name is Rafael. I am an electrical engineer, linguist, and bilingual teacher of mathematics and physics. And in this video, I would like to invite you to a conversation about the algebra of complex numbers. And for this purpose, I selected 14 questions. Let's begin the discussion with question 1. Question 1 says, what is the solution to the equation x squared plus 16 equal to 0? This is the question. Let's go to the solution. Initially, we isolated the quadratic term. In this way, x squared plus 16 equal to 0 becomes x squared equal to negative 16. At this point, a fundamental question arises. Is there a real number whose square is negative? The answer is no. The square of a real number, whether positive or negative, is always a positive real number. Thus, the equation x squared equal to negative 16 has no solution in the set of real numbers. To overcome this limitation of the set of real numbers, we must consider a broader set, the set of complex numbers. Let us define I squared as the imaginary unit and I equal to the square root of negative 1 as the basis of imaginary numbers. With this definition, we can return to solving x squared equal to negative 16. Taking the square root of both sides, x is equal to plus minus the square root of negative 16. Observe the number inside of the radical. It is a negative number. Let's decompose it. It becomes plus minus the square root of 16 times negative 1, which can be converted to plus minus the square root of 16 times the square root of negative 1. The square root of 16 we know, and it is 4. X is equal to plus minus 4. And how about the square root of negative 1? We defined it as I. In this way, the solutions to this equation are x1 equal to 4i and x2 equal to negative 4i. These are the solutions to the equation x squared plus 16 equal to 0. Therefore, we find that x equal to 4i and x equal to negative 4i are the solutions of the equation x squared plus 16 equal to 0. This equation has no solution in the set of real numbers, but it admits two solutions in the set of complex numbers. x1 equal to 4i and x2 equal to negative 4i are purely imaginary numbers, since the real parts are 0. And it is all for the debate of exercise number 1. Let's go to the next. Exercise number 2. What is the solution to the equation x squared plus 2x plus 10 equal to 0? This is the question. Let's go to the solution. To find the solution to this equation, we can use the quadratic formula. The quadratic formula is x is equal to negative b plus minus the square root of b squared minus 4 times a times c divided by 2 times a. For this exercise, negative 2 plus minus the square root of b squared minus 4 times 1 times 10 divided by 2, which can be simplified to negative 2 plus minus the square root of negative 36 divided by 2. Observe that the delta is negative. The delta is equal to negative 36. Take a look at this. Once again, we reach a stage of the solution in which we must extract the square root of a negative number. And as seen in the previous exercise, this is not defined in the set of real numbers. Thus, we must use the imaginary unit. In this way, the square root of negative 36 can be decomposed into the square root of 36 times negative 1, which is also equal to the square root of 36 times the square root of negative 1. The square root of 36 we know, and it is equal to 6. And the square root of negative 1 is I. Returning to the solution, we find therefore that x is equal to negative 2 plus minus 6i divided by 2, which is also equal to negative 1 plus minus 3i. In this way, we find that the solutions to this equation here are negative 1 plus 3i and negative 1 minus 3i. Observe the solutions. The numbers x1 equal to negative 1 plus 3i and negative 1 minus 3i are complex numbers with a real part and an imaginary part. The real part of each of them is negative 1, and the imaginary parts are 3i and negative 3i. Numbers of the form x1 equal to a plus bi and x2 equal to a minus bi are called complex conjugates, in which the real part is the same and the imaginary parts are symmetric with respect to the real axis. And this is all for the debate of exercise number 2. Let's go to the next. Exercise number 3. Determine the values of a and b that satisfy the equation 3a minus 2 plus 2b plus 1i equal to 7 plus 5i. This is the question. Let's go to the solution. Two complex numbers are equal if and only if the real parts are equal and their imaginary parts are equal. In this way, the real part 3a minus 2 has to be equal to 7. 3a has to be equal to 9, from which we get that a is equal to 3. The imaginary part 2b plus 1 has to be equal to 5. In this way, 2b will be equal to 5 minus 1, which is equal to 4. From this step, we get that 2b is equal to 4, b is equal to 2, a is equal to 3, and b is equal to 2. We conclude, therefore, that a equal to 3 and b equal to 2 are the values that satisfy the equation. And this is all for the debate of exercise number 3. Let's go to the next. Exercise number 4. What is the result of the sum 7 plus 3i plus 2 minus 5i? This is the question. Let's go to the solution. The addition of complex numbers is performed component by component, which means that we sum the real part of one with the real part of the other, and the imaginary part of the first with the imaginary part of the second. In this way, the real part is 7 plus 2 equal to 9. And the imaginary part will be 3i minus 5i equal to negative 2i. Therefore, 7 plus 3i plus 2 minus 5i is equal to 9 minus 2i. We conclude that this sum results in 9 minus 2i. And this is all for the debate of this exercise. Let's go to the next. Exercise number 5. What is the result of the subtraction 4 minus 6i minus 1 plus 2i? This is the question. Let's go to the solution. As for the addition, the subtraction of complex numbers is performed component by component. Therefore, the real part will be 4 minus 1 equal to 3, and the imaginary part, negative 6i minus 2i is equal to negative 8i. We conclude that 4 minus 6i minus 1 plus 2i is equal to 3 minus 8i. And this is the result of the subtraction, and it is all for the debate of this exercise. Let's go to the next. Exercise number 6. What is the value of z in the expression z equal to 2 plus 3i plus 5 minus I minus 1 plus 4i? This is the question. Let's go to the solution. We must carry out the operation component by component as we did before. In this way, the real part will be 2 plus 5 is equal to 7 minus 1 is 6. The imaginary part, 3i minus I is equal to 2i minus 4i is equal to negative 2i. We conclude therefore that z is equal to 6 minus 2I. And this is the solution of the exercise, and it is all for the debate of this exercise. Let's go to the next. Exercise number 7. What is the value of z in the expression z is equal to 3 plus 2i times 1 plus 4i? This is the question. Let's go to the solution. Multiplication follows the distributive law. What does it mean? It means that we multiply every element of the first complex number with every element of the second complex number. In this way, z is equal to 3 times 1 plus 3 times 4i plus 2i times 1 plus 2i times 4i. Continuing, z is equal to 3 plus 12i plus 2i plus 2 times 4 is 8. I times I. Remember that I squared is equal to -1. This becomes a negative number. Z is equal to 3 plus 14i minus 8. And the result will be -5 plus 14i. And this is the solution of the exercise. Z is equal to -5 plus 14i. And this is all for the debate of exercise number 7. Let's go to the next. Exercise number 8. What is the value of z in the expression z equal to 5 plus 2i divided by 2 minus I? This is the question. Let's go to the solution. To solve this problem, we must express the division of complex numbers in a form in which the imaginary unit does not appear in the denominator. For this purpose, we use the fact that the product between two complex conjugates always results in a non-negative real number. Thus, we multiply the numerator and the denominator by the complex conjugate of the denominator. This procedure eliminates the imaginary part of the denominator, thus rationalizing the expression. Observe that the multiplication of a complex number with its complex conjugate is a real number. A plus bi times a minus bi is equal to a squared plus b squared. We are going to use this property. In this way, z equal to 5 plus 2i divided by 2 minus I will be multiplied by 2 plus I divided by 2 plus I. Observe that we are not altering the number, we are multiplying by 1. This divided by this is 1. Whenever we multiply a number by 1, we are not altering it. The numerator five times 2 plus 5 times I plus 2i times 2 plus 2i times I. And this is equal to 8 plus 9i. Now the denominator. 2 minus I. Multiplying 2 plus I, we saw here that it results in a real number, and the real number is 2 squared plus 1 squared, which is equal to 5. In this way, we find that z is equal to 8 plus 9i divided by 5, or if you prefer, 8 divided by 5 plus 9 divided by 5i. And this is the value of z. And it was what the exercise wanted us to calculate. And it is all for this exercise. Let's go to the next. Exercise number 9. Determine the value of z3 equal to z1 times z2, given that z1 is equal to 3 times the cosine of 20 degrees plus I sine 20 degrees, and z2 is equal to 2 times the cosine of 50 degrees plus I sine 50 degrees. This is the question. Let's go to the solution. The complex numbers z1 and z2 are presented in their trigonometric form. To solve the problem, we can use the polar form as an intermediate step. The polar form of z1 is equal to 3 phase 20 degrees, and the polar form of z2 is 2 phase 50 degrees. We want z3. z3 is equal to z1 times z2. Observe this operation. When two complex numbers are expressed in polar form, the product is obtained by multiplying their magnitudes and adding their phase angle. In this way, z3 will be 3 times 2 phase 20 degrees plus 50 degrees. We discover therefore that z3 is equal to 6 phase 70 degrees. And this is the polar form of z3. We want the trigonometric form of z3. The trigonometric form will be 6 times the cosine of 70 degrees plus I times the sine of 70 degrees. And this is precisely what the exercise wanted us to calculate. And it is all for the debate of exercise number 9. Let's go to the next. Exercise number 10. Determine the values of z3 equal to z1 divided by z2, given that z1 is equal to 4 times the cosine of 100 degrees plus I sine 100 degrees, and z2 is equal to 2 times the cosine of 40 degrees plus I sine 40 degrees. This is the question. Let's go to the solution. As we did before, we will use the polar form as an intermediate step. The polar form of z1 is equal to 4 phase 100 degrees, and z2 is equal to 2 phase 40 degrees. We want z3. z3 is the division between z1 and z2. z3 is equal to 4 phase 100 degrees divided by 2 phase 40 degrees. Observe this expression. When two complex numbers are expressed in polar form, their division is obtained by dividing their magnitudes and subtracting their angles. In this way, Z3 is equal to 4 divided by 2, phase 100 degrees minus 40 degrees. And this is equal to 2 phase 60 degrees. Now we convert to the trigonometric form. Z3 is equal to 2 times the cosine of 60 degrees plus I times the sine of 60 degrees. And this is precisely what the exercise wanted us to calculate. And it is all for exercise number 10. Let's go to the next. Exercise 11. Convert the complex number z equal to -1 plus the square root of 3i to trigonometric form. This is the question. Let's go to the solution. To convert z equal to -1 plus the square root of 3i to its trigonometric form, we can use the polar form as an intermediate step. In polar form, a complex number is expressed as z is equal to the magnitude of z with an angle in which if z is equal to a plus bi is the Cartesian form of the complex number, the magnitude of z is equal to the square root of a squared plus b squared, and the angle is the inverse tangent of b divided by a. Let's use the values provided by the exercise. The magnitude of the complex number is equal to the square root of -1 squared plus the square root of 3 squared, and this is equal to 2. How about the angle? Phi is the inverse tangent of the square root of 3 divided by -1. Observe these results. Since the real part is negative and the imaginary part is positive in the Cartesian plane, the point lies in the second quadrant. Thus, the angle is the inverse tangent of negative square root of 3, which is equal to 120 degrees. Therefore, z is equal to 2 phase 120 degrees. And the trigonometric form is 2 times the cosine of 120 degrees plus I times the sine of 120 degrees. Observe this. And this is all that the exercise wanted us to calculate. And it is all for the debate of this exercise. Let's go to the next. Exercise 12. Convert the complex number z equal to 5 times the cosine of 30 degrees plus I times the sine of 30 degrees to Cartesian form. This is the question. Let's go to the solution. To convert this complex number to its Cartesian form, we simply need to know the values of the cosine of 30 degrees and the sine of 30 degrees. Considering that the cosine of 30 degrees is equal to the square root of 3 divided by 2, and the sine of 30 degrees is equal to a half, the complex number thus becomes z is equal to 5 times the square root of 3 divided by 2 plus I times a half. In this way, we find the solution of the problem. Z is equal to 5 times the square root of 3 divided by 2 plus 5i divided by 2. And this is what the exercise wanted us to calculate, and it is the solution of this exercise, and it is all for the debate of exercise number 12. Let's go to the next. Exercise 13. Write the complex number z equal to 4 times the cosine of 150 degrees plus I times the sine of 150 degrees in exponential and Cartesian form. This is the question. Let's go to the solution. To perform the conversion, observe that z equal to the magnitude of z times e raised to the power of I times phi is the exponential form of the complex number, and the magnitude of z in an angle is the polar form of the complex number, and the magnitude of z times the cosine of the angle plus I times the sine of the angle is the trigonometric form of the complex number. Thus, the exponential form is z is equal to the magnitude 4 times e raised to the power of I times 150 degrees. How about the polar form? The polar form is z is equal to the magnitude 4 in the angle 150 degrees. To convert it to Cartesian, we have to know that the cosine of 150 degrees is equal to negative square root of 3 divided by 2, and the sine of 150 degrees is equal to a half. We need to know this to convert to Cartesian. Therefore, to convert it to the Cartesian form, z is equal to 4, which is the magnitude. We are using here times the cosine of the angle negative the square root of 3 divided by 2 plus I times the sine a half. And this is equal to negative 2 times the square root of 3 plus 2 times I. And this is the solution of this exercise, the exponential form and the Cartesian form. And this is all for the debate of exercise 13. Let's go to the next. Let's go to the last exercise. Let's go to exercise 14. Determine the trigonometric and exponential forms of the complex number z equal to negative 2 minus 2i. This is the question. Let's go to the solution. We must recall that the polar form of the complex number z is equal to the magnitude of z in an angle. Likewise, the exponential form of the complex number is the magnitude of z times e raised to the power of I times phi. Let's work with the magnitude. The magnitude of the complex number is equal to the square root of negative 2 squared plus negative 2 squared, and this is equal to 2 times the square root of 2. How about the angle? The angle is the inverse tangent of negative 2 divided by negative 2, and this is equal to the inverse tangent of 1. Observe these results. Since above the real and imaginary parts of the complex number in Cartesian form are negative, the point lies in the third quadrant. We therefore understand that the angle phi is equal to 225 degrees. In this way, the polar form of the complex number is the magnitude 2 square root of 2 phase 225 degrees. And the exponential form, the magnitude 2 times the square root of 2 times e raised to the power of I times 225 degrees. And the trigonometric form is 2 times the square root of 2 times the cosine of 225 degrees plus I times the sine of 225 degrees. And this is all that the exercise will allow us to calculate, and it is all for the exercises. Now let's see some graphs. Now let's understand how to convert from one form to the other. Conversion from Cartesian to polar. If z is equal to a plus bi, the magnitude of z will be the square root of a squared plus b squared, and the angle is the inverse tangent of b divided by a. The conversion from polar to Cartesian. If z is equal to the magnitude of z phase phi, a is equal to the magnitude of z times the cosine of phi, and b is the magnitude of z times the sine of phi. To finish the discussion about complex numbers, let's understand the importance of the complex conjugate of a complex number. In the Cartesian form, if z equal to a plus bi is a complex number, its complex conjugate will be z equal to a minus bi. In the polar form, z is equal to the magnitude of z phase phi, and the complex conjugate of z is the magnitude of z phase negative phi. The multiplication of a complex number with its complex conjugate in the Cartesian form is a plus bi times a minus bi is equal to a squared plus b squared, and in the polar form, the magnitude of z phase phi times the magnitude of z phase negative phi is the magnitude of z squared. Observe that the multiplication of a complex number with its complex conjugate will result in a real number. And this is all for the debate of the algebra of complex numbers. And it is all for this video, my friends. I hope you enjoyed watching it and learned from it. I am a teacher, guys. If you want to book a lesson with me, use my WhatsApp number. Goodbye!